Welcome to the deep dive. Today we're getting into something pretty cutting edge, AI web agents.
Mm-hmm.
These aren't just your standard large language models.
Yeah.
They actually, use tools, web browsers, code interpreters to solve really complex multi-step problems.
Right. And we're focusing today on how you actually train these things effectively.
Right.
We're basing this on a single, really dense research source that introduces a new method called Agentic Entropy-Balanced Policy Optimization, or AEPO.
AEPO, okay. And this is all within the world of Agentic Reinforcement Learning.
Exactly. Agentic RL, that's the framework that lets these models learn over these long, complex tasks. And a key concept here is entropy.
Entropy, right, the uncertainty signal. If the model doesn't know what tool to use next or which action to take, high entropy flags that uncertainty.
Yeah, and typically that's seen as a good thing. It encourages the agent to explore, to try different branches.
Seems logical. Explore when you're unsure.
It does, but here's the twist the research highlights. Leaning too heavily on that high entropy signal can actually backfire. It can cause something they call training collapse.
Training collapse. So the very mechanism designed to help it explore ends up breaking the training.
Pretty much. We need to unpack why that happens.
Right.
The goal in training, it's pretty standard RL. You want to maximize your reward, get the right answer eventually, while also keeping the agent's behavior, its policy, somewhat close to a reference model you started with.
Using its available tools, of course.
Right. The tools are fixed, but the sequence of actions, the path, isn't. And that path uncertainty, the entropy, is meant to be the guide.
Okay. So standard RL says uncertain, branch out. But the paper says this causes problems, two distinct problems, right, at different stages.
Yes, exactly. Two key challenges. The first one happens during the sampling or rollout phase. They call it high-entropy rollout collapse.
High-entropy rollout collapse. What's going on there? Why does high entropy cause a collapse in exploration?
Well, the issue isn't just high entropy itself. It's that these high uncertainty decision points, these tool calls, often happen one after another, consecutively.
Ah, so it's like a chain reaction of uncertainty.
Sort of, yeah. The model hits one uncertain step, branches, hits another uncertain step almost immediately on that same branch, and keeps going down that single rabbit hole.
And it just keeps digging deeper on that one uncertain path.
That's what the data showed. They found that 56.5%, over half of these high entropy tool call steps, were consecutive. It's transitive.
So it gets fixated. What does that do to the overall exploration?
It kills the diversity.
Yeah.
Think of it like having a budget for exploring different routes. This consecutive branching uses up almost the entire budget on just one or maybe a few very deep, uncertain paths.
Okay, so it's spending all its exploration money in one place.
Right. And the result, according to the paper, was that a staggering 93.4% of the branches ended up concentrated on just 1 to 3 trajectories.
Wow, 93.4%. So all the other potential paths just get ignored.
Completely neglected. That's the collapse. The exploration becomes incredibly narrow, which really undermines the whole point of using RL for these complex problems. You've exhausted your options before you've even seen most of the possibilities.
That definitely sounds like a collapse. Okay, so that's the sampling problem, but there's a second challenge, right, happening later during the learning phase.
Yes, this one's about the policy update. It's called the high entropy token gradient clipping problem.
Gradient clipping.
Okay.
So this is about how the model learns from the samples it collected.
Exactly. It's a learning issue. Now, those high entropy tokens, the points where the model was uncertain, are often really important. They might represent, a key logical step connecting different ideas or the actual decision to use a specific tool. These are valuable learning moments.
These are the signals that could teach the agent how to explore or reason better.
Precisely. But standard RL algorithms, well, they have this mechanism called gradient clipping, mainly for stability.
Right, to stop the learning steps from being too large and destabilizing the model.
Correct. But the problem is, vanilla clipping is often indiscriminate. It aggressively reduces or clips the learning signal, the gradient associated with these crucial high-entropy tokens.
So even if the agent made a really smart exploratory move at a point of high uncertainty and it led to a good outcome, the standard algorithm might just ignore that signal.
It often does. It suppresses that valuable learning signal, sometimes right from the beginning of training. The model takes a useful risk, it pays off, but the learning mechanism effectively censors that success.
Which means the model can't properly learn from its most insightful, uncertain decisions. It gets stuck.
Yeah, the paper calls it fixed paradigmatic reasoning. The agent learns one way to think about the problem and has trouble adapting or finding better strategies, even if the initial sampling, however flawed, contained hints of them.
Okay, so we've got sampling collapse limiting diversity, and then gradient clipping stopping the model from learning from the interesting bits it did find. That sets the stage for AEPO.
Exactly. AEPO is designed as a two-pronged solution to tackle both of these entropy-related problems.
Let's break it down. First, how does AEPO fix the rollout collapse, the sampling issue? It uses something called the dynamic entropy-balanced rollout mechanism.
Right. It starts before sampling even begins, with what they call entropy pre-monitoring. It's like a quick assessment.
An assessment of what?
It looks at the initial question the agent is trying to answer and measures its inherent uncertainty. Let's call it the root entropy. Then it compares that to the average uncertainty expected when the agent actually starts using its tools, the average tool call entropy.
Ah, interesting. So it's comparing the uncertainty of understanding the problem versus the uncertainty of executing the solution.
That's a great way to put it. And based on the gap between these two entropy measures, it dynamically allocates the total sampling budget.
How does that work?
Well, if the initial question itself is very uncertain, high root entropy, the agent needs to explore broadly. So more budget goes to global samples, trying different high-level approaches. But if the question is clearer, but using the tools is expected to be tricky, high average tool entropy, then more budget shifts towards deeper, more focused branch sampling along specific paths. It's smarter resource allocation.
That makes sense. But how does it stop that chain reaction, the consecutive high entropy steps?
That's the second part of the rollout mechanism, the entropy-balanced adaptive rollout. It introduces a branch penalty.
A penalty.
Yeah. If the agent starts going down a path with multiple high-entropy steps in a row, this penalty kicks in. It progressively decreases the probability of taking yet another high-entropy branch along that same specific uncertain chain.
So it actively discourages the agent from getting obsessed with one uncertain path. It forces it to spread its bets a bit more.
Exactly. It pushes the agent to look elsewhere, ensuring a wider range of paths get explored, addressing that collapse issue directly.
Okay, so that's the rollout fix. Now, what about the learning side, the gradient clipping problem? AEPO has the entropy climbing balance mechanism for that.
Right. This tackles the issue of suppressing those valuable learning signals from high-entropy tokens.
We know standard clipping just reduces the gradient if it's outside a certain range. How does AEPO change that?
It uses a technique involving a stop gradient operation, but essentially what it does is this. When the agent takes a high-entropy action, and that action leads to a positive outcome, a positive advantage, AEPO modifies the clipping.
Modifies how?
Instead of clipping the gradient down, potentially to zero, it preserves it. It actually ensures the gradient is retained and even slightly scaled up to something like 1 plus epsilon.
So it specifically identifies these good high uncertainty steps and says, no, we need to learn from this one fully. It bypasses the usual clipping restraint for these specific cases?
Precisely. It allows the policy to climb the gradient from these positive exploratory signals. And to make sure this is done smartly, it also introduces entropy-aware advantage estimation.
Advantage estimation.
Yeah.
That's usually about judging how much better an action was than expected, right? Often just based on final accuracy?
Correct. Standard RL might just look at whether the final answer was right. AEPO reshapes this advantage calculation.
How so?
It adds another component based on the entropy, specifically the change in entropy. The idea is to give a higher advantage, a bigger learning signal, to tokens that were not only correct, but also occurred at points of high uncertainty.
Ah, I see. So it's not just rewarding correctness. It's explicitly rewarding being correct when you are uncertain. It directly reinforces successful exploration.
That's the goal, rewarding beneficial, high-risk, high-reward actions.
Okay, this whole AEPO approach, managing the rollout diversity and then carefully handling the learning signals from uncertain steps, sounds much more nuanced. But does it actually work better? The paper claims it beat 7 other RL algorithms across 14 datasets.
Yeah, the results look quite strong, especially on challenging benchmarks designed for deep information seeking. Things like GAIA and WebWalker QA, these require a lot of tool interaction.
What kind of scores did AEPO get?
Using a powerful model, Quinn 314b, AEPO hit a pass at one score, meaning getting it right on the first try, of 47.6% on GAIA and 43.0% on WebWalker QA. These are tough tasks.
Those sound pretty good. How does that compare to other methods, particularly other Agentic RL methods?
That's where it gets interesting. Compared to ARPO, another decent Agentic RL baseline, AEPO showed significant gains. For instance, with a slightly smaller model, Quen38B, AEPO had an average improvement of about 6% on GAIA and WebWalker QA over ARPO.
A 6% average jump on hard tasks is definitely notable. It suggests the entropy balancing isn't just theory.
Right, it translates to real performance gains. And they also looked at paths at K, what happens when you let the agent try multiple times.
Ah, so seeing if it finds more correct answers if given more chances. What did that show?
It showed AEPO scaling really well. When they increased the sampling to pass at 5 with the 14B model, the scores jumped significantly, 65.0% on GIA, 70.0% on WebWalker QA.
That implies AEPO isn't just finding one good path more reliably, but it's actually finding a more diverse set of good solutions.
That seems to be the case. And it connects back to the rollout mechanism. They actually analyzed the sampled trajectories.
What do they find?
AEPO samples formed more distinct clusters, 62 cluster centers, compared to only 54 for the ARPO baseline.
More clusters means more diversity in the explored solutions.
Exactly. It showed the branch penalty and the pre-monitoring were working, forcing the agent to cover more ground instead of getting stuck. In some tests, it explored all potential paths, whereas the baseline often missed many.
Okay, performance is up, diversity is up. What about efficiency? These agents can be expensive to run, right?
Yeah.
Lots of tool calls.
That's a huge factor and maybe one of the most impressive results. AEPO achieved its superior performance using only about half the number of tool calls compared to the standard RL methods, even ones optimized for clipping.
Half the tool calls.
Yeah.
That's massive. That could drastically cut down training and deployment costs.
It really could. It makes using these advanced agents much more practical.
And the last piece, stability. Was the training process itself smoother with AEPO? Did the entropy balancing help there?
Yes. They tracked the entropy levels during training. AEPO showed a much more stable, less erratic entropy curve compared to the other algorithms.
So no wild swings in uncertainty.
Fewer, yeah. The finding was that simply maximizing entropy wasn't the goal. Having sharp fluctuations was actually bad. What worked better was maintaining a reasonably high but stable entropy level throughout training that seemed to correlate with better, more consistent performance improvement.
Okay, so let's try and wrap this up. AEPO tackles this paradox where entropy, meant to help exploration, ends up causing problems. It does this with a two-part fix.
Right. First, it manages the rollout phase using pre-monitoring to allocate the budget smartly, and penalties to prevent fixation on one uncertain path. That ensures more diverse sampling.
And second, during the learning phase, it fixes the clipping problem. It makes sure the model can learn from valuable high uncertainty steps if they lead to good outcomes, using that entropy-aware advantage.
Exactly. It shifts exploration from being just, random branching based on uncertainty to being a more controlled, learned, and rewarded behavior. The result seems to be better performance, higher efficiency, and more stable training for these complex web agents.
It really reframes how to think about uncertainty in these systems. And it leaves you with a final thought, doesn't it? Considering how AEPO uses that difference between the question's uncertainty and the tool use uncertainty to guide exploration, how might that principle change the way we train models more broadly, especially around deciding when to rely on their internal knowledge versus when to actively go out and use a tool like a search engine?
That's a really interesting point to ponder. It certainly suggests a more dynamic way to balance internal reasoning and external information gathering.